Hey everybody, we're going to go through just some of the main, some of these ideas about multiple linear regression, and we'll flesh the ideas out more in class. Of course, the book goes into far more detail than this lecture will. So the idea, now the setting is that you have a response variable and you have two or more predictor variables that you want to consider for a more complicated model, for modeling the value of your y variable, your response variable. So so we're going to say, for example, here that you have p of them, x1, x2, all the way up to xp, where p could be 3 or 5 or whatever. So the multiple linear regression model is going to be y equals b0, which is your intercept, so to speak, and then b1 x1 plus b2 x2 all the way up to bp xp. So we're adding all of these in a linear fashion. So we're going to look at a couple of cases where multiple linear regression would be useful. It's actually a vastly useful method in statistics. So for one example, we're going to be looking at in this course, estimating the association between the response variable and a primary predictor, and then you can adjust for possible confounding variables. So you can see if there's other variables that, when we say confounding variable, excuse me, some third variable that is correlated with both, but is somehow the value of the third one influences both the x and the y variable, and so we'll see what we could do with this, how we handle confounding variables. Sometimes they're called lurking variables, and then constructing a model that effectively explains the observed variation in the response. So these are a couple of the applications. So let's look at fitting and interpreting the multiple regression model. So statins are a class of drugs that are widely used to lower cholesterol. So it followed the recent guidelines for prescribing statins would lead to statin use in almost half of Americans 40 to 75 years of age, and nearly all men over 60. A few small studies have suggested that statins may be associated with lower cognitive ability. The PREVEND study collected data on statin use as well as other demographic factors. So we've looked at the PREVEND data set. We're going to see have statin use as a second predictor for your RFFT score. So the RFFT score, here we're showing a scatter plot where we have in red, we have the statin users, and in blue, we have the non-statin users. And so what we are interested in seeing is if we can see what is the effect of using statins on somebody's RFFT score. This is something that we'll look at in lab, and so you could on the one hand you could just split your data into two groups and you could come up with two linear models, but each model is going to have a much smaller sample size, and so instead what you can do is have a fuller model where you have two predictors, statin use and age. And you can use all the data to fit the full model. So here's an example, just looking at the mean, or actually I guess it's the median is the line, the RFFT score distribution for statin users and non-statin users. Of course, it's worth thinking about this, that statin is used more so by older people, right? If you look back at this histogram or the scatter plot, you'll see that the red dots tend to be on the right-hand side of the scatter plot, not on the left-hand side, right? Because as it said, it's for lowering cholesterol, and so it's something that usually is prescribed for older people. So this is how you would you would in R fit a linear model. What you do is you just as before, so this is the simple linear model, just fitting the RFFT use on whether or not someone uses statin. So so what we have is a very, very simple model where it's just you have your predicted RFFT score is going to be the intercept minus 10.05 if the person is a statin user or not. Okay. Now this is a simple linear model, but the predictor here is a categorical variable rather than a quantitative variable. So really the statin user is either going to be a yes or a no. Okay, so we'll look through that statin use example more in detail later. Okay. All right. So so the statistical model for multiple regression, like we said, where we have P predictors. So each B coefficient is the predictor for the corresponding predictor variable. So what that means, what we would interpret that as implying, that coefficient is the average change in the y variable with a 1 unit change in that particular x variable if the other values of the predictors remain constant, if they don't change. And so the idea is that this is the effect of this one particular predictor adjusting for the effects of the other predictors. So let's look at what the multiple regression model would look like for RFFT and modeled using both statin use and age. So in R, you build your linear model by putting addition, like plus symbols, between your predictors. So it's RFFT squiggle is going to be explained by statin plus age. That's the way the syntax you use in R. And it's going to give you the coefficients for the intercept, for statin user, and for age. So now you see if you're controlling for age, statin user, like if a person uses statin, that actually leads to a slight increase in their RFFT score. And here is, if you were to print the full details for the coefficients, what you'll see in addition are you get t scores for each of your estimates as well as a p-value. This is going to be important when we are looking at these models, especially since they have larger and larger number of predictors. What we'll be looking at is if one of these predictors has like an insignificant p-value. And now you have to kind of parse through all of these exponents, but this for statin user, that's so the 7.43 times 10 to the negative 1, that's actually a 0.74. That's actually a very, very high p-value. So if you have age in your model, then statin user, whether or not someone uses statin, would not end up being a significant predictor. Okay, so in other ways we can evaluate your multiple regression model once you build it. So you're going to need to check the assumptions, and the assumptions are linearity, that for each predictor variable, a change in the predictor is linearly related to a change in the response variable, as long as the other values of the other predictors remain constant. Now in practice, it actually can be hard, that can be actually unrealistic, because sometimes the predictor variables, one predictor could not be held constant because there's actually some sort of dependency between the predictors. That could happen. Anyway, we have constant variability, that the residuals should be have approximately constant variance, right, regardless of the predictors, and that they should be normally distributed, and that the samples are drawn they're independent of each other. Okay, that's going to be checked based on the design of the study that produced the data. You can use the residual plots to check some of these, but it's not really possible to make a scatter plot of the response variable against several simultaneous predictors. So what you can do is you can look at you could either look at lots of different scatter plots, a scatter plot for each pair of predictor, each predictor with the response variable. You can like look at all the different scatter plots to see linearity, or you can plot the residuals against each of the predictors. And so, as long as it's a numerical predictor, you can see and make sure there's no pattern or curvature or something that would indicate nonlinearity. For constant variability and normality, you can use the same methods as simple linear regression. For constant variability, you want to make sure that the spread on this residual plot doesn't change, and you want to, for normality, you can again use the normal probability plot for the residuals. So we'll be using R squared to kind of rate how good our model is, this multiple R squared, just as we did with simple linear regression. The more variables you put into a model, really R squared is only going to increase. So you could never end up have R squared going lower, decreasing with more models. Basically, R squared is going to be the coefficients. The way that the math works underneath the surface is the coefficients of the predictor variables are chosen in such a way as to maximize R squared. And if one of the variables shouldn't be in the model, then its coefficient is going to be close to 0. And so, but still, R squared can never be hurt by adding more variables. But just adding a ton of variables isn't always a good idea. You end up making a very complicated model, which maybe you raise your R squared, but you end up making your model less generalizable. So, and this is a problem because if you fit your data if you fit your model too strongly to the data, then the model can A, be not easy to interpret, and B, it's not going to be useful for predictions for new cases. So you want your model to be as simple as possible, but you want R squared to be as high as possible at the same time. So you do have this balancing act. The adjusted R squared is a good tool for this. So the adjusted R squared is calculated by taking the so you adjust this ratio of the variance of the residuals to the total variance by n-1 over n minus p-1. So that n-1 is going to be greater than n minus p-1. P is the number of predictors in your model. So what you're going to do is you're going to be slightly inflating that depending on how large your model is, like how many predictors it is. Also with respect to like how big your sample size is. And then that's subtracted from 1. So the adjusted R squared is going to be useful. There's a bit of a penalty in the adjusted R squared for including predictors that do not contribute too much towards improving your R squared, towards like explaining the variation. So this is a great tool for to kind of balance the predictive ability of the model with the complexity of the model. And that's always the balancing act that you're interested in for these multiple regression models. It doesn't have the same straightforward interpretation as it's not the. It really just has to be thought of as it's like the adjusted ratio of variance that's explained, but the adjustment is. It's not a clear. It can't be like clearly stated like exactly what its adjustment is. It would suffice it to say though, it gives a penalty for a more complicated model. So when we have categorical predictors, before we were looking at statin use, and that was either a yes or a no. So you could see it makes sense to just you have your typical individuals, and then for those who are users of statin, you add a different or subtract a different number. That's the coefficient for that. Now, if you have this, so that's what you call a binary predictor, right? It has two levels, and And so that's essentially going to estimate the difference in the mean response between the two groups. So here, since the mean RFFT score for the individuals who are not using statins was 70.71, the mean RFFT score for individuals who are using the statins, it's 10.05 lower. That's the meaning of this model, right? Okay, so if there's more than two levels, what we do is now we have to encode these levels somehow. And the most common way to do it is to convert the different levels to values. Now, one way to do it is if you have an ordinal variable, it's one thought might be, okay, you could just assign them 0 to, let's say this is looking at someone's education level. 0 for primary school, 1 for lower secondary school, 2 for higher secondary education, 3 for university education, 0, 1, 2, 3. And so what we end up, what we've done then is, well, we're just encoding encoding this as, it's still if you are careful to encode it as a factor in R, then you're not just converting it to a number. What we're going to do is you'll see, so yeah. We'll talk about the details on this in a sec. This is just first visually, you can see for the RFFT score, if you look at the distributions for the different education levels, it does seem like there is a linear trend between them. So, and certainly there is a difference between these education levels. So if we were to, use the education interpreted as a factor, all right, what the model is going to produce for us. So we're saying RFFT explained by education only. What we have is the model is going to be the intercept plus these adjustment terms only depending on what the education level is. So if a person has lower second, you'd be adding 14.77857, or if their education was higher second, you'd be adding 32.13345. Or if they're in education university, you'd add 44.96389. Now, we're not using the value 0, 1, 2, 3 as a quantitative variable. We're not. We don't want to assume that the slope is perfectly linear for like different levels of education, because converting an ordinal to a truly quantitative variable is a no-no. But we do see that there does seem to be roughly about a 15, increment of about 15 or so per level of education, which is interesting. But this is going to allow for let's say university ended up giving them a bonus of 60 or 70 on their scores, right? This would allow for any coefficient for lower second, higher second, and university. Now, and one thing that I haven't mentioned is like the first level, the 0 level, is sort of absorbed into the intercept. So that would be your kind of baseline. Your baseline would be for individuals who have primary education only. So as I said, the baseline category is individuals who at most completed primary school. Intercept is the sample mean for those individuals. The coefficients represent the change when you go from primary to these other levels of education. So 14.78 points is the average increase in RFFT score for someone if they've gone from primary to lower secondary education. An increase of 32.13 is the average change for a change from primary to higher second, and so forth, right? So inference, for inference, we have to think back to the idea that this model is an attempt to estimate a relationship that really exists in reality. And in reality, we go with this kind of assumption that if there is a linear relationship, it looks like this. Y is beta 0 plus beta 1 x1 plus all the sums up to beta p xp, all the way to the epsilon, this error term, which is again a normally distributed random variable with a standard deviation that's fixed, some sigma value. And so when we are estimating these slope parameters, and potentially, we're estimating also the intercept, but usually we're not doing inference on the intercept. We're determining whether there is really enough evidence to conclude that this slope is non-zero. This is what the hypothesis test for one of these, just like one of the coefficients would look like. The null hypothesis is that this particular coefficient, this slope coefficient, is 0. So in other words, the two variables, the xk variable and the y variable, have no association. And the alternative is that the coefficient is non-zero. So some association. You can calculate a test statistic for this, and actually it's a t-statistic. It can be calculated by looking at you get the degrees of freedom. That's the sample size minus the number of predictors minus 1, and the way you calculate t. Now it's your bk, your estimate divided by the standard error of bk. Now the standard error of bk is not something that you can calculate very easily without R, but you'll see in the output that the t statistic is exactly the estimate divided by its standard error. And so since you know the standard error, you can calculate confidence intervals easily by just figuring out a t star for a 95 or a 99 or whatever size confidence interval you're interested in, and times the standard error, and that'll give you a margin of error. So so this t statistic can lead you to calculate a p-value as well. So you can determine whether or not each of these particular slopes or coefficients is statistically significant or not. And then there's one other. The other inference is whether or not altogether a linear model is even appropriate in the first place. And to do that, you actually are going to be calculating an F-statistic from an ANOVA table. So it's going to be based on, essentially it's going to be based on the sum of the squared residuals and how that relates to the sum of the squared values of y. And so it's comes from the same numbers where the r squared comes from. But anyway, we'll get into that a little bit more later. The question is, are all the coefficients 0 or not? The null hypothesis is a way of taking the null assumption that none of the variables have any relationship with y. So beta 1 equals beta 2 equals beta 3 equals all of them just equal 0 is the null hypothesis. And the alternative is that just at least one of them doesn't equal 0. So the alternative is just there is some relationship between some of the variables. And so if you get a F statistic that has a p-value that's smaller than alpha, whatever alpha you use, then you're going to reject the null hypothesis. And the F statistic comes from an ANOVA table, and we'll talk about that in lab. So here we're in the results from doing a regression, you are going to see the F statistic down at the bottom. So you can see it's 73.3, and it has 2 degrees of freedom. It has a numerator degree of freedom, 3, and a denominator degree of freedom of 496. And both of those two, depending on the numerator, the 2 degrees of freedom, the distribution shape of the F statistic changes. So you need both of those, but R does that for you, and it gives you the p-value. And the p-value is basically 0. Also, you can see for each of the particular estimates, all of these estimates are significant. One helpful thing is R is going to put stars next to the p-values depending on how small they are. And 3 stars is very, very significant, meaning extremely strong evidence that this estimate is non-zero. Now, you can get an ANOVA table out of your regression. And the ANOVA table is going to, instead of having, the numbers are going to be similar to the ANOVA we've looked at for comparing multiple means. Actually, in this particular one, since we're grouping our data into, we have 4 groups and comparing 4 different group means, this is actually precisely the same ANOVA table that you would get from if we were doing the ANOVA, a one-way ANOVA. It is actually a one-way ANOVA, but it's just done under the guise of a linear regression. Because we're explaining our y variable based on a categorical variable with 4 levels, this is completely equivalent to doing an ANOVA, a one-way ANOVA, explaining where we're modeling our y over 4 different groups, right? So we're looking at 4 different group means. Anyway, you can see the F statistic is there. It's calculated. It's the mean squared for the model divided by the mean square for the residuals. And the larger that is, the more significant our results are. And you can get this pairwise, do a pairwise t-test to see if all of them are statistically, all of the coefficients are statistically different from each other. So if we were to do a full model for this RFFT so here we're modeling RFFT by 3, actually here we're adding a 4th predictor as CVD. This is the results of what this regression would look like. So it looks like what I tend to look down through and see like which of the predictors is the most significant and least. So it looks like again, whether or not the person uses statin, it seems to be not very significant. It's just slightly over 0.05. So there would be like, it could be justified to actually drop that from your model. Though you might keep it just because it is a strong predictor. But maybe it's not. You couldn't be totally sure that it is a true predictor. But in this case, you do have a lot of strong predictors for RFFT, and you can see that we've got, with all of these together, the R squared comes to 0.4355, which is not bad considering it's hard to predict someone's intelligence score. So then there's this concept of interaction. So the way that we've been looking at this model so far, that when one of the predictors changes by 1 and we hold the other variables constant, that's the way we interpret the slope term. An interaction occurs when this assumption is not true and there is actually going to be, it's when there's a dependency between the 2 variables. So you can actually look at a very complicated interactive model, but we'll look at 2 variables that have an interaction. So if we look at let's look at a linear model that we're trying to predict somebody's total cholesterol from whether or not they have diabetes and what their age is. And so here you can see this is the model. When we say the expected total cholesterol, that's the model where we drop off the error term, right? On average, because the expected value of the error term is 0. So the average total cholesterol is just going to be beta 0 plus beta 1 times age plus beta 2 times whether or not they have diabetes. Yes, so you add beta 2 if they have diabetes. If not, you don't add on beta 2. So here's, based on this data, this NHANES data sample of 500 adults, we get this, the intercept is 4.8, the age coefficient 0.00749, and then the total cholesterol, if they have diabetes, you would be subtracting 0.317 from their total cholesterol. Here we're looking at the scatter plot, and if we were to do and we can actually plot the two lines on here for those who have diabetes non-diabetics are blue and then diabetics are in red. Okay. Now, if we are looking at cholesterol versus age, if we were to just take out the just to do separate the group into two, right? We had your diabetics and your non-diabetics in two different groups. You get a very different story that you get, right? For diabetics, you actually have age decreasing the average cholesterol, but for non-diabetics, you have age increasing the total cholesterol. Okay, so something funny is happening, and it turns out that there is a relationship or an interaction between age and whether or not people have diabetes. So yeah, I mean, if you were to plot both of these lines in the combined group, you get a very wacky different. In order to kind of have the full model capture this sort of a shape, what we're going to have to do is somehow capture this interaction between age and diabetes. The way we do that is we add a third predictor. The predictor is going to be age times diabetes. So in fact, it's going to be, we'll have an additional beta 3 that's going to be for those who have diabetes. It's going to modify the age slope by beta 3. So if you rerun this model with this interaction term, and this is the way you do it, you actually so the total cholesterol, you put the squiggle and you say age star diabetes. What that does is it creates a model using all of the possible interactions between age and diabetes. And here, so and plus the individual terms as well. So you have age, you have diabetes, yes, and then you have age and diabetes together. And what you get is this model where it seems like that for non-diabetics the age slope is 0.009, but for diabetics we would adjust that slope by negative 0.03, so it ends up being a negative slope. Right. So essentially you can see by plugging in diabetes, like 1 for diabetes, yes, the linear model becomes 6.42 minus 0.024 times age. But for when a person's not diabetic, then this becomes 4.7 plus this slope of 0.0096. So these interaction terms you're able to create a single model using all of the data, rather than splitting the data into two parts where you have half the data creating one model, half the data creating another model. Whenever you can have a larger sample size to create a single model, that's better than splitting your data in half and creating two separate models. And you can, again, you can do inference to look at the significance of your interaction term here. The interaction term has those 2 stars. It has a p-value of 0.00665. That's really low. So you would say, yes, there's definitely a significant interaction. Now, for explanatory models, in explanatory modeling, the goal is to construct a model that explains the observed variation in the response variable as best as possible. So the idea is you want to have this idea of a parsimonious model, a model that explains as much of the variation as possible with as few predictors as possible. So you want to have the model be simple as possible while still being really useful. There's different methods of model selection, and we'll talk about a few of them. But the idea is like to kind of add or remove predictors one by one until you're happy with what you get in the end. So we're not going to go into all of it, but generally you want to start with kind of exploring the data and thinking about what predictors are likely to be useful, and you have start with some initial model, and you fit an initial model with the predictors that seem like they're best predictors, and then you can sort of if you're using your adjusted R squared as a guide, you can add or remove, and you can see if you have you can either remove predictors that are not significant or add new predictor, and see if you keep improving your adjusted R squared, then you're on the right track. Once you get to a point where you can't improve your adjusted R squared anymore, then you probably want to stop. That's the idea. And we'll look at this in Lab 5. I think that's all that I'm going to say now. I think it's pretty good. Okay, so this is a good overview of the kinds of things we'll be concerned with multiple regression, and well,